We continue from last lecture. We do force between a point charge and a finite rod uniformly distributed charge. So what's the force on the point charge due to the line charge? Last time we used table of integrals, but today we do mathematically. Of course, the result will be the same. This is the rod. This is the midpoint, so a point charge Q1 is on this perpendicular bisector. Half of L here. Half of L here. The total charge on the rod is Q2. The point charge is Q1. The force on this charge, due to the symmetry of the problem, the force on Q1 cannot be towards the left side. Similarly, the force on Q1 cannot be directed to the right-hand side, cannot be this way, because the picture is symmetrical. So we will conclude the force on Q1 is along the vertical perpendicular bisector. If we call this y-axis, the force is along the y-axis. Let's divide the rod into many small sections. Call this section delta x. This is delta x. This is x. As you understand, delta x is a small increase of the variable x. We will find the force between this small charge and Q1. Let's call this small charge delta Q. What is the force between delta Q and Q1? How big is delta Q if the total charge of the rod is Q2? We use proportion. What is delta Q? The length of delta Q, the length of this section is delta x. The whole rod, the charge is Q2. And Q2 is over the entire length, which is L. So let's say this again. For the entire length L, the charge is Q2. For a small section delta x, what is the charge delta Q? Proportion. Divide, equal. So, delta Q is Q2 multiply delta x over L. This has the meaning delta Q is what? Is total charge divided by total length. This fraction is charge per unit length. But my length is delta x. Therefore, what's the charge over the small section delta x? Of course, it's charge per unit length times the length of the small section. That's exactly what this means. The force between delta Q and Q1 is along the line joining them to this direction. So call this delta F. Delta F, Coulomb's law. Q1 delta Q divided by this length. Let's call this R, the square of the distance. Coulomb's law. Next, let's cut the total length into many, many small sections like this. Many, many. How many? N. Okay, N. Okay, let's write here the N sections. N is the number of small sections. Now, what we do is to make the small section very, very short. Make delta x very small, which means the number of sections is very, very large. So when n approaches infinity, many, many small sections, which also means delta x approaches 0. We will do this. If we do this, then the label delta becomes D. In the limit, this is the sense of limit Yeah, in the limit n goes to infinity, which also means delta x becomes 0. In that limit, the delta can be written as d. So we change delta to d. Delta q is this. So now the delta becomes d. Therefore, I can rewrite this q1 here. q2 over L. I put L below, and delta becomes d when we make delta x approaches 0 and n approaches infinity. So this. Remember, delta f is this way. Therefore, df is also this way. But we argued that the result is that the force is only vertically up. Therefore, what I want is this component. Call this delta fy. Now, we already changed the delta to d, so I want dfy. How do I find the y component? I need a variable theta, which is, of course, this angle. The relation between delta f and delta fy is cosine. So I need a factor cosine theta. Now you see I have variable x, I have variable y, variable r, I also have variable theta. The next step should be integration, but I cannot integrate over 3 variables. So I need to change the 3 variables to only 1 variable. The 1 variable, we choose theta. Q1, Q2, L. How do we change R to theta? R and theta is here. Look at this right triangle. This distance is fixed. Let's call this distance y. Then the relation between r and y is r cosine theta, or r is y secant theta. R is squared. So I have theta, y is a constant. Now I need to change x into the variable theta. X is here. Theta is here. Y is constant. X divided by y is tangent theta. Therefore, x is y multiplied tangent theta. X equals y multiplied tangent theta. Then dx is y d tangent theta. What is d tangent theta? D tangent theta is secant square theta d theta. So I put this here in the numerator. Dx is y secant theta d theta. Oh, secant square theta d theta. Okay. This y cancels the square there. Secant square cancels the secant square. So I have dfy equals let's see, is it k q1 q2 l and y, and I cosine theta d theta. Now I have only one variable. Then the next step, I can do integration. Now the left-hand side becomes fy. So right-hand side, I can move all the constants in front of the integration sign. K, Q1, Q2, L, Y, they are all constants. So the integration is this. What are the limits of integration? We must look at the variable theta. So from this end to this end, so the theta is from this theta to this theta. You see the theta, the lower limit and the upper limit have the same magnitude, right? This angle and this angle hem, same magnitude, except one is negative, the other one is positive. Suppose I call this theta 0. Now, suppose I call this theta 0. Suppose I call this theta 0. Then, of course, this is also theta 0. So my limit is negative theta 0 to positive theta 0. Then we can use the same argument as last lesson. Cosine theta is an even function. You integrate an even function from negative a to positive a, the result is just 2 times the integration from 0 to positive a. So let's write that. From negative theta 0 to positive theta 0 is 2 times from 0 to positive theta 0. Integration of cosine is sine. When you put the lower limit 0 into sine theta, so that is sine 0. Sine 0 is just 0. Then put the upper limit there is sine theta 0. What is sine theta 0? Look at this right triangle. Theta 0 is this. Theta 0. Sine is this. L over 2 divided by this length. But this length is y squared plus L over 2, the whole thing squared. And take square root, right? So I have so finally I have this. Sine theta 0. That's the opposite side, that's hypotenuse. Now 2 cancels this 2, L cancels this L, therefore my Fy is finally, okay, let me erase this. Okay, Q1, Q2, Y this is my final answer. Actually, I can erase my subscript y because this is the answer. It's not just a y component, it is the answer. So I can erase the subscript y. The force on Q1 due to a uniformly distributed Q2 over a length L is this. And this is exactly the same as before, the last lecture, just using the table of values, table of integrals. Okay. This example is finished. So first we try table of integrals, and then we do mathematically using the theta as a variable. So we are discussing examples about Coulomb's law. And next we will have more examples using Coulomb's law. So next example is a charged ring. If you have a uniformly charged ring and there is a point charge on the axis of the ring, so what is the force on the point charge? Then after that, we will have another example. If you have a disk, circular disk, which is uniformly charged, and between this disk and a point charge on the axis of the disk, so what is the force? So we will have more examples after this lesson. Thank you. Goodbye. See you next time.